In this video, I want to give a visual and mathematical approach of how waves are propagating in a medium where the refractive index is frequency dependent. The phenomenon that you can see here is called dispersion. A wave can be described by a simple wave function u equals kx minus omega t, where k is the wave number, the number of whole oscillations that can fit between 0 and 2 pi, and omega the angular wave frequency. On the left, you can see a wave propagating over time. Next, let's have a look at only two overlapping waves before we go to the more complicated cases. To illustrate this nicely, the two waves have different wave numbers. At this point, a small mnemonic aid. You could still estimate the wave number when you would freeze the video, but you would not be able to see the frequency anymore. First, let's have a look at case 1. Wave A has a high frequency and wave B has a low frequency. And now case 2. Wave A has a low frequency and wave B has a high frequency. Now we want to describe the frequency-dependent behavior with the refraction index. As the wave number is a little bit unintuitive, we replace it by frequency over phase velocity. Next, we replace the phase velocity by the definition of the speed of light in vacuum divided by the refractive index. And there we have it, the refractive index in our formula. Using Euler's formula, we can rewrite this expression with an E function. The term dispersion makes only sense when we look at many waves with different frequencies. So we can now build a wave parcel by summing over the sum frequencies. On the right side, you can see 121 frequencies. The more frequencies you add, the sharper will be the pulse. And now we let the wave parcel propagate with different dispersion relations. What we see is the following. When the derivative of the refractive index in respect of the frequency is constant, the wave parcel maintains its shape. When it is positive, the high frequencies travel faster. When it's negative, the low frequencies travel faster. Some examples where you have dispersion phenomena in nature are, for example, waves, thunder, or light propagation in gas. Where you luckily don't have dispersion is, for example, a sound wave in air over a small distance.